Okay.
All right. Hi, the paper that we are covering in relation to in-memory compute utilizes a ferroelectric FET-based cell design that exploits both hybrid bit precision for both training and inference of a deep neural network. In-memory compute is the idea of storing data into RAM to run calculations entirely in computer memory rather than in outside databases that may run on slow disk drives. As opposed to conventional von Neumann hardware architecture, which can be limited by data transfer speeds between memory and compute nodes, in-memory compute has computation done at the location of the data itself. This can be valuable as in-memory computing can be used to accelerate training and inference of deep neural networks, or DNNs, by parallelizing operations such as multiply and accumulates, which are pretty common operations for neural networks. Thus, the motivation being to accelerate computation associated with DNNs, which requires a certain level of bit precision to properly accumulate the weight changes during incremental MAC operations. The goal is to propose an analog synaptic weight cell that can take advantage of both volatile and non-volatile operation with hybrid bit precision in order to perform training and inference for a DNN.
And so we know that in memory computing, in order to boost the computation speed, we usually done the computing process inside the data storage block rather than other part of the cell, since it doesn't need to pick the data through long wires or buses that will cause some noise on it. And after computing is finished, the non-volatile memory are used to store the result called the weight in DNN and other training method, and those weights are represented as the analog conductance value for the given pulse number of voltage. And in the previous days, people used the resistive RAM, and the phase change memory to preserve the data. But however, these devices suffer from some unacceptable accuracy degradation due to asymmetry weight update or limited dynamic range. And so the FeFET design is popped out and it uses partial polarization switching to provide higher symmetry weight update. And the training accuracy increases significantly, but it also leads to a more sophisticated peripheral circuit design. And yeah, so next. So in this picture, we can see some previous work of the people in NVN. And the first one is the filamentary RM. And since it has excessive nonlinearity between the positive and negative updates, the accuracy here is very low. It's just 41%. And for the next generation of interfacial RM, the accuracy has been improved to 73% with better linearity, but the pulse width here increased to milliseconds due to a slow diffusion of vacancies or ions. And so it comes out with the FeFET device, and it provides highly symmetric weight update leading to a 90% accuracy. But since it used the non-identical pulse and it increased the peripheral circuitry complexity, and so our work is the 2T1FeFET and use the modulate of the gate voltage of the FeFET to represent the linear update of the LSB during training, and MSB are stored by polarization states of the FeFET for inference.
So the analog weight cell proposed by the paper combines two CMOS transistors, being one PMOS and one NMOS, with an FeFET, where the gate of the FeFET is connected to the shared source drain diffusion regions of the CMOS transistors. This way, the gate voltage of the FeFET can be modulated, which allows for control over the LSBs of the weight by charging and discharging through the gate, through the CMOS transistors, while keeping the FeFET in a triode region. During the weight update, pulses are then applied to the gates of the PMOS and NMOS at the GP and GN nodes respectively for positive and negative updates to the LSBs while keeping the CMOS transistors in the saturation region, which ensures that the charging and discharging current is independent of the gate voltage of the FeFET. The idea being here is to have a balanced charging and discharging current in order to have symmetric positive and negative updates to the LSBs of the weight. So the figures shown here illustrate the primary schemes in which the weight bits are encoded. In figure A on the left, you can see that by modulating the gate voltage, the LSBs are linearly encoded to the resulting channel conductance of the FeFET. The MSBs are then encoded to different FeFET polarization states without overlapping the LSBs within each MSB state. The example given in figure B here shows the case of a 2-bit MSB, which corresponds to 4 polarization states, where the gate voltage is in the range VA to VB, which is constrained by the linear region overlap of multiple polarization states, which determines the number of update steps corresponding to the bit width of the LSBs. Lastly, the figure on the right, figure C, shows different scenarios of updating the weight LSBs and MSBs. Looking at the VG curve, the blue curve, if the gate voltage increases above the VB limit, the resulting drain current becomes larger than the reference current, which requires a move from the S1 polarization state to the S2 state to transfer the weight information to the MSBs. Then the LSBs can be updated continuously within the S2 state, and you can reset the gate voltage to the level that maintains the drain current in order to prevent the same drain current in order to prevent information loss to the LSBs or of the LSBs. Conversely, if the gate voltage drops below the low limit VA, which corresponds to the drain current decreasing below the reference current, the FeFET requires a programming towards the back down to the S1 polarization state. You can see on the image on the right, the positive and negative updates to the LSBs through the application of pulses applied at the gates of the P and N MOS. Again, the goal here being to balance the charging and discharging in order to have symmetric positive and negative updates to the LSBs of the weight. So this flow chart here shows the control flow of training for the DNN network using the proposed FeFET synaptic weight cell. For each training batch, you first update the LSBs by applying charging or discharging pulses to modulate the gate voltage based on the value of the incremental weight change calculated using a stochastic gradient descent based backpropagation algorithm. Because of the limited range of the gate voltage and also due to capacitor leakage, the LSB information is occasionally transferred to the LSBs to prevent data loss. So for every n batches, you transfer the weight by programming the FeFET to the corresponding polarization state according to the readout current. After the weight transfer, the gate voltage is reset to the level that maintains the same channel conductance in order to recover the residual information of the LSBs. With the caveat here being that it would require a high precision ADC, which should ideally have the same bit width as the weight itself, which would be both area and power hungry. As a result, the solution is then to reset the gate voltage to the midpoint between the VA and VB, which trades off area and power for a slight potential residual error.
So now comes to the implementation of our design, which is a 6-bit synapses weight cell with 2-bit MSBs and 4-bit LSBs. And the method is used in that the FeFET will utilize the multi-domain polarization switching in the ferroelectric gate to tune the threshold voltage, and by this method, it will produce the different programming ports to obligate. And this FeFET model consists of BSIM4 base MOSFET model and the switching by the precision dynamic model. And the C figure shows on the left is the hysteresis loop of the model that represent the different polarization state of the cell. And the 2-bit MSB serve as the different polarization charge that result in 4 state, which is 0, 0, 0, 1, 1, 0, 1, 1. And these states are determined by the difference post of the input. And yeah, and the post and this post value is due to the difference of the threshold voltage of the FeFET dielectrical material. And we can see that the B picture on the left and the right, it shows that the dynamic range of the gate voltage is set to be 1.44 to 1.76 voltage, and with a pulse width we given 5 nanoseconds, and this will lead to a delta VG of 20 millivolts per update pulse, and since and this means that a 4-bit LSB can be achieved since that we cut this range into 16 pieces of different voltage. And here the figure here is the summary of the operation of 2T1F cell. And we can see that for the update of LSBs, the V1, V2 means the voltage for charging, discharging using the pulse input. So we want to charge the cell, we put a pulse in the gate of the PMOS. And if you want to discharge, we put the pulse to the gate of the NMOS. And for the update of MSBs, V1, V2 represent the voltage for programming and erasing operation respectively. Okay, so from the left figure, we can see that after doing the design, it shows a much improved symmetry and linearity between the positive update and negative update of the 6-bit synapses realized by the 2T1F cell. But however, since in the practical circuit, charging and discharging current will not be always the same due to some external factor. And so the delta VG per update pulse isn't the same at every VG, and thus result in a slightly nonlinearity. But fortunately, this difference is only like 5% of one LSB updates, and so like 20 millivolts times 5% is like 1 millivolts, shown on the picture on the right top. So the weight update here is still symmetric as well. And so we can see that this model has performed a much better symmetric and linear than other NVN device introduced at the previous slide, and it shows at the right bottom of the slides. Okay, so after so here comes the results, and we put by incorporating the 6-bit 2T1F into the Hsien training in this case, and we can see that the accuracy can reach to 98.3%, and it's only a 0.2% difference compared to the ideal software training for the MINUS data set. And we believe that this difference between those two is because the different delta VG in the practical circuit that described in the last slide are due to this slightly difference. And despite of that factor, and however, other factors will also affect the training accuracy. And one of them is the residual errors that caused by the occasional weight transfer of the 6-bit 2T1F cell. And we can see that on the left picture, and as the gate voltage goes high, the time we need for gate voltage to leak for one LSB step is getting higher and higher. And for example, in the inset of the picture, we need 1.64 milliseconds to leak when our gate voltage is 2 volts, 2V. And this leads to a relatively small number of the transfer interval. And we calculated in roughly the 230 batches in the interval in this case. And on the right figure, we can shows that if the higher number of the transfer interval is, the higher accuracy you can get in training the model. And with 100 batches, we can only reach to 96%, but with 300 batches, we can achieve a 98% accuracy. And the reason that the larger interval is better is that because if the absolute accumulated delta delta W weight within one transfer interval is less than half of one MSB step, and equals to 8 LSB steps. And this will fail to trigger an MSB state to change, and the weight will be reset back after the weight transfer, and the gate voltage will be reset to middle of VA plus VB as aforementioned. And so we can see that for the left figure, the interval with 100 batches will gain roughly a 35% of accumulated weight after done the third time wafer transfer. And while the interval with 100 batches only has less than 5%, and this fails to flip the MSB state, so it leads to a lower accuracy. And despite using the additional to using the large interval, we also use another way is to add a little variation on the polarization state to conquer this error. And we can see that a small variation, less than 5%, does not hurt the accuracy, as it may help on compensating the residue error caused by non-ideal weight transfer. But it will give a bad effect on accuracy if we add this variation too large, and for example at over 10%. And since the term we had add has changed the value of the original polarization state. And so here's for so finally we compare our 2T1F design with other memory design. And the first one is for the ITIC structure, which is a totally volatile capacitor-based design. And since it's volatile, it couldn't support the inference. And for the second work, it combines with 2 PCM and a 3 transistor 1 capacitor structure. And although it is suitable for both training and inference, however, and due to its circuit complexity, it somehow ends up with a larger energy consumption in larger area. And this indicates that our design has the largest benefit for training the model.
So that's the general idea of the 2T1F ferroelectric FET based weight cell that was proposed by the paper. We did have some critiques given the information that was presented. Some of them being, we thought that the readers may have benefited from a physical or layout representation of the proposed weight cell, which would show the connections and the relationship between the CMOS devices and the FeFET itself. Also, a more detailed explanation between the relationship between the gate voltage and the channel conductance would have been useful, which would better explain the methodology in which the LSBs are encoded, as well as the encoding for the MSBs using the polarization states of the FeFET. In addition, a more quantitative comparison of the performance of the proposed weight cell against a volatile memory Synapse would have been more interesting to see. They could have compared them based on speed and power consumption and also learning accuracy to see the benefits of using non-volatile memory over volatile memory for on-chip memory. In general, though, between the proposed weight cell and the previous weight cells that were given in the table in one of those first slides, it would have been beneficial to see power and energy and area characteristics for each one of those, which would include probably dynamic and leakage power, which would have been useful for consideration of maybe an area or an energy constrained use case in using any of those given cells. Here are the references that are first given by the paper that we were presenting today, and then a couple of sources that we used to bolster our understanding of the material. And thank you. That is our presentation. All right.
All right.
That is